Hey guys, here's another AP Physics 1 review session video. This topic today is on rotation. I want to focus just on the big ideas and what these things are in terms of relation. Really, the ideas in rotation in this unit should not be anything that crazy or new, because all we're taking is ideas from everything we've done previously and then applying it to a rotating reference frame. Now the difference between this and uniform circular motion is this can have something that changes in its spin rate. So to clarify some ideas, we want to make sure that we're okay with. We just want to use some symbols and ideas to talk about. First thing, theta is angular displacement. Omega, angular velocity. Alpha, angular acceleration. Those are basically the linear motion parts there. You can think of that being like x, v, and a. And for that, we have those kinematic equations for rotational stuff. Now, we can use it when things are just spinning or whatever, but when things get real interesting is when we talk about the ideas of a rotating pushing force making something spin faster or slower. What is that idea? Torque. Now, you see, torque is equal to I alpha. Similarly, F is equal to ma. That's rotational inertia. Remember, a whole bunch of examples which we looked at in class, it's based upon not just the mass of the object, but where that mass is located. We looked at a whole bunch of different things. A hoop with the mass on the outside has a large rotational inertia, so it's difficult for it to start moving as opposed to a solid disk. It's also more difficult to stop moving. So that's talking about the change in its spin rate. That's the rotation inertia, and that's the torque. The weird part with torque is we can link it to linear stuff by having some weird problems. And these are some things that we looked at before. By having an object that's like this and we have something attached, it's fixed about this point. We talk about things spinning or trying to spin. Ultimately, in terms of perpendicular forces here I could say this is a steel bar, there's a cable attached here to a wall, there's a fixed point here. The thing itself would have some force of gravity this way. This thing's going to have a tension this way. Say, well, isn't that old stuff? Really, we can look at this in terms of torques as well. Say if it's not accelerating, that means that the total net torque on this thing is indeed equal to 0. So that means that we have torque Fg plus minus torque tension. And we can work it through that way. There's a lot of problems that you see very similar to that with that type of setup. The other part with this stuff in terms of torque and things that makes things weird is when we talk about the ideas of momentum. Now, old linear momentum ideas are P equals mv. Well, in terms of an angular sense, L is equal to I omega. The rotation inertia multiplied by the angular velocity. Just like with momentum, mass times velocity. So again, all this stuff is not new, it's just looking at things in a rotating reference frame. Now, one common theme is trying to link the ideas of energy to rotating motion stuff. And with that, rotational kinetic energy is 1/2 I omega squared. So what does that mean? If we look at the ideas of kinetic energy from before, it's 1/2 mv squared. The inertia times the velocity. In terms of rotational, it's 1/2 I omega squared. We talked about some very specific ideas with this. We said, okay, if I have something that's spinning and rolling down a plane like this, how could I find its velocity at the bottom? Or what's going on? Ultimately, at the top, it has some PE, it has some potential energy. Okay, the kinetic energy, potential is the only thing that has the bottom. At the top, excuse me. At the top, it's going to have kinetic and rotational kinetic. So how can we use this? The initial energy in the system is equal to the final. So U is equal to K plus KR. Say, well, won't it just be moving energy? Translation means straight line motion. We both straight line motion as well as spinning rotational motion. So U equals K plus KR. So that MGH is equal to 1/2 mv squared plus 1/2 I omega squared. Now, I'm looking at that, it looks like I have some bunch of crazy stuff. If it's just an object going around, a fixed point, Depending on the moment of inertia, we can calculate a couple of ways. One common way to see this is mr squared for just an object about a point. We can see things in terms of fixed points. Maybe 1/2 mr squared, something like that. We can plug that in here. But if you notice, the masses would then cancel out. We have to use a relationship dealing with translational, meaning straight line motion stuff, and stuff spinning. We need to know this. V equals r omega. It's a common way to relate rotational and straight line velocities. It's not an equation that's listed on the AP equation sheet, but it's something that you should indeed know. Now, if you notice, it seems like I'm skimming through the ideas of rotational motion. It's because it's not super crazy. It's simply focusing on ideas that we've seen before foundationally and applying it to a rotating reference frame. So instead of x, we've got theta. Instead of v, we've got omega. Instead of a, we've got alpha. Instead of F for force, we have tau for torque. Instead of m, we get I for inertia. L for angular momentum. And yeah. The other thing that we saw too was the idea of conservation of angular momentum. L naught is equal to L. As the figure skater problem, right? If they spin, if they're initially spinning with some speed and a large rotation inertia with their arms out, and they bring their arms in, they're going to go ahead and spin faster. Angular momentum needs to be conserved. Again, in that, the angular momentum stays conserved, and what's happening? Rotation inertia decreases, angular velocity increases. As always, thank you. See you in the next video.